Welcome to the representation theory course. This is the 20th lecture. So in this lecture we are going to start representation theory of symmetric groups. We know for a finite group there is a one-to-one correspondence between conjugacy classes and the number of equivalence classes of irreducible representations. However, this bijection between these two sets is not explicit in an arbitrary situation. We are going to see that for symmetric groups there is an explicit bijection between a conjugacy class and the corresponding irreducible representation of the symmetric group. So we need this very beautiful idea of what we call partition. Partition functions appear naturally in number theory and various other contexts. Let n bigger than or equal to 1 an integer. A partition of n is a tuple. Let us denote it by lambda, and the tuple is lambda 1, lambda 2, so on, lambda L of positive integers such that lambda 1 is bigger than or equal to lambda 2, bigger than or equal to lambda 3, and so on, bigger than or equal to the last lambda L, and sum of all these lambda i's is n, and lambda 1 plus lambda 2 plus so on plus lambda L is n. So let us set one notation. We use this notation to denote that lambda is a partition of n. Let us see some examples. The tuple lambda equals to say 2, 2, 1, 1, 1 is a partition of 2 plus 2 plus 1 plus 1 plus 1. That is 7, is a partition of 7. Take lambda prime to be, let us say 6 comma 1. This is a partition of 7. Let us see for various values of n. If n is 1, then how many partitions n can have? It has to have only one partition. Then lambda equals to 1 is the only partition of 1. Let us take n equal to 2. If n equals to 2, then how many partitions n can have? Then look at this, n equals to 2 and mu equals to 1, 1 are all the partitions of 2. So n equal to 2 has 2 partitions. What about if n equals to 3? Then we could take lambda to be, of course, 3, or we could also take lambda to be 2, 1, or we could take lambda to be 1, 1, 1. These are all the partitions of n equal to 3. For a positive integer n, let Pn denote the number of partitions of n. The preceding examples show that P of 1 is 1, P of 2 is 2, P of 3 is 3, number of partitions of 4 is 5, and so on. Till date, no closed formula for Pn is known. There are various recursive formulas and various conditional formulas, expressions like the number of partitions where the entries are odds and so on, but no closed formula for Pn in general is known till date. So we are going to study this function from the point of view of representation theory of symmetric groups. Let us prove this theorem. The number of conjugacy classes in the symmetric group Sn is same as the number of partitions of n, that is same as P of n. Let alpha belong to Sn be a k cycle and tau belong to Sn any permutation. So let us write alpha, say alpha is this k cycle A1, A2 and so on, say AK, where A1, A2, AK are in the set 1 to n of which Sn is a permutation group. Then what is alpha of AI? Alpha of AI is AI plus 1 mod k, and consider tau alpha tau inverse. Tau of AI. So consider tau alpha tau inverse acting on tau of AI, which by definition is same as tau alpha of AI but alpha of ai is ai plus 1 mod k, that is tau of ai plus 1, where ai plus 1 of course we are reading mod k. So tau alpha tau inverse of tau ai is simply tau ai plus 1. What happens to the elements outside the set 1 to a1 to ak? Let L be an element in the set 1, 2, so on up to n minus a1 to ak. Then what does alpha do to this L? Alpha just fixes it, because alpha is a k cycle in which L doesn't appear. Then alpha of L is simply L, and what is tau alpha tau inverse of tau of this L? This by definition is just tau alpha of L, but alpha L is just, this is just tau of L. So tau alpha tau inverse map tau of ai to tau of ai plus 1, and it fixes everything outside this. So this implies that this permutation tau alpha tau inverse, first of all it's a k cycle, and the cycle is of the form tau of a1, tau of a2, so on tau of ak. So conjugate of a k cycle is a k cycle. This is the observation we have made. Now if beta is any permutation in Sn, if beta belong to Sn is any permutation, then we know that each permutation can be written as a product of disjoint cycles. Then beta can be written as beta 1, beta 2, and so on, some beta s, where beta i's are disjoint cycles of length bigger than equal to 2, because we don't really write the one cycles. Then look at this conjugate tau beta tau inverse. This is equals to tau of beta 1, beta 2, so on beta s into tau inverse. What we do is that between beta I and beta I plus 1 we introduce tau tau inverse. So therefore this can be written as tau beta 1 tau inverse, tau beta 2 tau inverse, and so on tau beta s tau inverse. From the first observation we know that tau beta 1 tau inverse is again a cycle of the same length as beta 1. Tau beta 2 tau inverse is again a cycle of the same length as the cycle beta 2, and tau beta s tau inverse is again a cycle of the same length of the cycle beta s. So the conclusion is that if we take any permutation and write it as certain product of disjoint cycles of certain lengths, then any conjugate of that will again be a product of disjoint cycles, and the length of the cycle will also be same. If beta I is a lambda I cycle, that is a cycle of length lambda I, then we say that beta, which is the product beta 1, beta 2, so on beta s, is of type lambda 1, lambda 2, and so on lambda s. Further, each conjugate of beta tau beta tau inverse of beta is again of type lambda 1, lambda 2, and so on lambda s. So if t equals to n minus s, then the type of beta, type of the conjugacy class of beta, gives the partition lambda 1, lambda 2, so on lambda s, and then you can write 1, 1, and so on 1 precisely t times, where we have arranged lambda 1 bigger than equal to lambda 2 bigger than equal to so on bigger than equal to lambda s and bigger than equals to 1. Because beta is a product of disjoint cycle beta 1 to beta s, they commute, so we can always arrange them in decreasing order of the length of the cycles. Thus we have shown that if beta is of type lambda 1 to lambda s, then any conjugate of beta is also of type lambda 1 to lambda s. If we can show that two permutations of the same type are conjugate, then each conjugacy class in the symmetric group gives a unique partition of n. Conversely, if I am given any partition of n, then I can take any cycle with that partition type and that will give me a conjugacy class. That will show that there is a one-to-one correspondence between the number of conjugacy classes in the symmetric group and the number of partitions of n. Let alpha and beta belong to Sn be two permutations of the same type, and let us write the type as lambda 1, lambda 2 and so on, let us say lambda s, where we can of course assume that lambda 1 is bigger than or equal to lambda 2 and so on bigger than or equal to lambda s, and each of course is bigger than or equal to 2 because we don't write one cycles. We claim that alpha and beta are then conjugate to each other. So let us write alpha as alpha 1, alpha 2, so on alpha s, and beta as beta 1, beta 2 and so on beta s, where alpha I and beta I are lambda I cycles for each I from 1 and s. Let us write the cycle alpha I and beta is explicitly. So let alpha I equals to a1 I, a2 I and so on. This is a cycle of length lambda I, so it is a lambda I, and similarly beta I as b1 I, b2 I and so on b of lambda I. To show that alpha and beta are conjugate, I need to find a permutation tau such that tau alpha tau inverse is beta. So define a permutation tau by tau of any a k I. It is simply corresponding b k I for all I bigger than or equal to 1, less than or equal to s, and for each k bigger than or equal to 1, less than or equal to lambda I. Further, assume that tau fixes any other element of the underlying set, which is 1, 2 and so on up to n. Thus tau is clearly a permutation of 1 to n. Now what is tau alpha tau inverse? This by definition is same as tau of alpha 1, alpha 2 and so on alpha s of tau inverse, and I can rewrite this as tau alpha 1 tau inverse and tau alpha 2 tau inverse and so on tau alpha s tau inverse. And by the preceding observation, the first part of this proof, we see that tau alpha I tau inverse is the cycle tau of a1 I, tau of a2 I and tau of a lambda I, but that I have set as b1 I, b2 I and so on b lambda I. So therefore this is just same as beta 1, beta 2 and so on beta s. So we have shown that if alpha and beta are two permutations which are of the same type, then they are conjugate to each other. And we have already shown that two permutations which are conjugate to each other, they are of the same type. Thus two permutations in Sn are conjugate if and only if they are of the same type, and therefore each conjugacy class determines a unique partition of n. Conversely, given a partition of n, we obviously get an element of the symmetric group and hence it gives a conjugacy class. This shows that there is a one-to-one correspondence between the number of partitions of n and the number of conjugacy classes in Sn. Therefore, the number of inequivalent irreducible representations of the symmetric group Sn is same as the number of partitions of n. So corollary, the number of inequivalent irreducible representations of the symmetric group Sn equals the number of partitions of n, that is P of n. We will find an explicit correspondence between conjugacy classes of the symmetric group, which are same as partitions of n, and irreducible representations of the symmetric group. For that, we need to develop a lot of machinery. So the first among them is Young diagram. What is a Young diagram? If lambda equal to lambda 1, lambda 2, lambda L is a partition of n, then the Young diagram of L consists of n boxes placed in L rows, where the ith row has lambda I boxes. Let us see an example. Take the partition lambda equals to say 4, 2, 1. Then lambda is a partition of 7. Then the Young diagram of the partition lambda is the following. It needs to have 3 rows, where the first row will have 4 boxes, second row will have 2 boxes, and the last row will have 1 box. This is the Young diagram of this partition lambda equals to 4, 2, 1 of 7. Take one more example. Let us say lambda equals to 3, 3, 2, 1, 1. Then lambda is a partition of 10. Lambda is a partition of 10, and the Young diagram of lambda is, so it need to have 3 boxes, 1, 2, 3. Second row will have again 3 boxes, 3. Third row will have 2 boxes. Fourth row will have 1 box, and the last row will also have 1 box. So 3, 3, 2, 1, 1. This is the Young diagram of the partition lambda equals to 3, 3, 2, 1, 1 of n equals to 10. Given a partition of n and its Young diagram, by looking at the Young diagram, we can construct another partition of n. So what we do is take the conjugate diagram, where the rows become columns and columns become rows. Conjugate partition. If lambda is a partition of n, then the conjugate partition, let us denote it by lambda t of n, is the partition whose Young diagram is the transpose of the Young diagram of lambda. Let us see an example. If we take lambda equals to 4, 3, 1, 1, then lambda is a partition of 9 and has Young diagram the following. The first row will have 4 boxes, second row will have 3 boxes, third row will have 1 box, fourth row will have 1 box. Then what is the transpose of this diagram, or equivalently the conjugate partition? The transpose of the above Young diagram is then the following. It has 4 boxes in the top row, and then 2 boxes in the second row, 2 boxes in the third row, and 1 box in the last row. And the corresponding partition is 4, 2, 2, and 1. So given a partition, we can obtain another partition called conjugate partition, and it's easy to see from the diagrams. Let us look at this image that I have taken from Wikipedia. So this image gives all the partitions of the integers up to 8. You can see from the image that if you reflect this image across the diagonal that go from southeast to northwest, then you see that the partitions on the upper triangular region are simply transpose of the partition in the lower triangular region. So roughly you need to just find half the total number of partitions that an integer can admit. The other half are simply the transpose of the given partitions. Now in order to understand partitions in depth, we need an order on the set of all partitions of a given integer called the domination order, and this order will help us in constructing the irreducible representation corresponding to a given partition. So let's do that. We are going to show that the set of all partitions of a positive integer has a partial order, and that order we call the domination order. So let lambda equals to lambda 1, lambda 2 and so on, lambda L, and mu equals to mu 1, mu 2 and so on, mu m be two partitions of n. We say that lambda dominates mu, written lambda bigger than or equals to mu if lambda 1 plus lambda 2 plus so on plus lambda I is bigger than or equals to mu 1 plus mu 2 plus so on mu I for every I bigger than or equal to 1, where if I become bigger than L, then we simply set corresponding lambda I to be 0, and if I become bigger than m, then we take the corresponding mu I to be 0. Very simple minded definition. In terms of the Young diagram, it says that if you are given two partitions lambda and mu of a positive integer n, you take the Young diagram of shape lambda and Young diagram of shape mu, then the number of boxes in the first row of lambda should be bigger than or equal to number of boxes in the first row of mu. Number of boxes in the first two rows of lambda should be bigger than or equal to number of boxes in the first two rows of mu. Number of boxes in the first three rows of lambda should be bigger than or equal to number of boxes in the first three rows of mu, and so on for each I, which is bigger than or equal to the maximum of L and M. Let us see some examples. Look at the partition lambda equals to 5 1 and mu equals to 3 3. Okay, then lambda and mu are partitions of 6. The Young diagram of shape lambda, or the Young diagram corresponding to lambda, is the following. So this has 5 boxes in the first row, 1 2 3 4 5, and 1 box on the bottom, whereas the Young diagram corresponding to this is mu is this one. Now the number of boxes in the first row of lambda is 5, and the number of boxes in the first row of mu is 3, so 5 bigger than or equal to 3, and the number of boxes in the first two rows of lambda is 6, and the number of boxes in the first two rows of mu is of course 6. This implies that lambda is bigger than or equal to mu. Notice that domination order is not a total order on the set of all partitions of n. You could have two partitions which are not related to each other. For example, take lambda to be 3 3 1, then lambda is a partition of 7, and take mu to be 4 1 1 1, mu is also a partition of 7. Then lambda, then what is the Young diagram of lambda? Or if you want, you can simply use the definition, or you can just check the diagram. This is the Young diagram of lambda, and the Young diagram of mu is this. Now you can see that the number of boxes in the first row of lambda is 3, where the number of boxes in the first row of mu is 4. So lambda is certainly not bigger than or equal to mu. Let's look at the other way. The number of boxes in the first row of mu is 4, which is bigger than or equal to number of boxes in the first row of lambda. That's fine. The number of boxes in the first two rows of mu is 5, whereas the number of boxes in the first two rows of lambda is 6. So that implies that mu is also not bigger than or equal to lambda. So lambda and mu are not related at all under this order. Next, we show that this order is indeed a partial order on the set of all partitions of n. The domination order is a partial order on the set of all partitions of n. Reflexivity of domination order is obvious. Also, if lambda is bigger than or equal to mu and mu is bigger than or equal to sigma, then lambda 1 plus lambda 2 plus so on plus lambda I is bigger than or equals to mu1 plus mu2 plus so on plus mu I by definition of the order. But mu1 plus mu2 plus mu I is bigger than or equal to sigma 1 plus sigma 2 plus so on plus sigma I, right, for every I, because it's just an inequality of positive integers. So this implies that lambda 1 plus lambda 2 plus so on plus lambda I is bigger than or equals to sigma 1 plus sigma 2 plus so on plus sigma I for every I, and this implies that lambda is bigger than or equal to sigma. Therefore, the order is of course transitive. It remains to show that the order is antisymmetric. We are going to show antisymmetry by induction on n. If n is equals to 1, there is nothing to do because there is only one partition of n. The conclusion is obvious. So suppose that n is bigger than 1, n is bigger than 1, let lambda bigger than or equals to mu and mu bigger than or equal to lambda. Let us say lambda equals to lambda 1 up to lambda L and mu equals to mu 1 mu m. Take I equals to 1, then lambda bigger than or equal to mu and mu bigger than or equal to lambda implies that lambda 1 is precisely same as mu 1. Because if we draw the Young diagram, it's saying that the number of boxes in the first row of lambda is bigger than or equal to number of boxes in the first row of mu and vice versa. But that means the number of boxes in the first row of both lambda and mu is the same. That is, lambda 1 is same as mu 1. Let us call it something as k. Then lambda 2, lambda 3 and so on up to lambda L, let us call it lambda prime. Then lambda prime and mu prime that I defined similarly as mu 2 so on mu m. They are partitions of what? They are partitions of n minus k, because I have thrown away the first factor. Are partitions of n minus k, which is of course less than n, so that I can use the induction hypothesis, where this less is the usual order on integers. Now since lambda 1 plus lambda 2 plus so on plus lambda I is same as mu 1 plus mu 2 plus so on plus mu I for every I, because we are given that lambda bigger than or equal to mu, so therefore lambda 1 plus lambda 2 plus lambda I is bigger than or equal to mu 1 plus mu 2 plus mu I and vice versa. So therefore they are equal for every I, but lambda 1 is same as mu 1, we cancel it off, which implies that lambda 2 plus lambda 3 plus so on plus lambda I is same as mu 2 plus mu 3 plus so on plus mu I for every I. What does this imply? This implies that for the new partitions lambda prime and mu prime, we have lambda prime is bigger than or equal to mu prime and mu prime is also bigger than or equal to lambda prime. But lambda prime and mu prime are partitions of n minus k, which is strictly less than n. So by induction hypothesis, this implies that lambda prime is same as mu prime by induction. But once lambda prime is same as mu prime, that implies that lambda equals to mu, which implies that lambda equals to mu. And hence, this domination order is a partial order on the set of all partitions of n. Let me discuss some examples here. Let us take n equals to 2. If n equal to 2, then we know there are only two partitions of 2. One is just 2 and other partition is 1 comma 1. And if you want the domination order, then we know that this partition is bigger than or equals to the second partition. Lambda is bigger than or equal to mu, because the first row of lambda has more elements than the first row of mu, and the first two rows of lambda has the same number of elements as mu. Let us take n equals to 3. Now I am not going to write partition, I will simply write the corresponding Young diagrams. Look at this partition of 3, then we know that this partition of 3 is bigger than or equal to the second partition of 3, and which is certainly bigger than or equal to the last partition, the vertical partition, which is actually conjugate of the first one. Let us look at n equals to 4. So, look at this partition of 4, which is just 4. This is bigger than or equals to this partition of 4. This is bigger than or equals to this partition of 4. This is bigger than or equals to this partition of 4, and this is bigger than or equal to the partition 1 1 1 1. Let me conclude with one more example. N equals to 5. This is the partition of 5. This is bigger than or equal to the second partition, where you have 4 boxes in the first row and 1 box in the second row. This is bigger than or equal to the third partition, where you have 3 boxes in the first row and 2 boxes in the second row. And this is bigger than or equals to where you have 3 boxes in the first row, 1 box in the second row and 1 box in the third row, which is bigger than or equal to this partition, where you have 2 boxes in the first row, 2 boxes in the second row and 1 box in the third row, which is bigger than or equals to where you have 2 boxes in the first row, 1 box in the second, 1 in the third and 1 in the fourth, which is certainly bigger than or equal to the partition 1 1 1 1 1, which has 1 box in each row. I will stop here. In the next lecture, we are going to develop some more background before proving the explicit bijection between conjugacy classes in the symmetric group and the irreducible representations of the symmetric group. Thank you.